Section: Introduction. In this section, we discuss the significant progress made in the field of large vision language models, LVLMs, thanks to the remarkable achievements of large language models, LLMs, and advancements in vision language pre-training. We've managed to create sophisticated LVLMs by combining powerful vision encoders with LLMs, which allows us to bypass the need to build these models from the ground up. These LVLMs have shown outstanding performance in various multimodal tasks, proving their ability to understand, reason, and apply knowledge across different contexts. Unlike traditional methods that fully fine-tune the entire model, recent studies have started to keep both the vision encoder and the LLM unchanged during the training of LVLMs. This approach is based on two main reasons. First, vision encoders and LLMs already possess a strong capability to extract features and reason, thanks to their extensive pre-training on high-quality data. Fine-tuning them might result in losing this valuable knowledge. Second, as these base models grow in size, keeping them fixed during training helps reduce the computational costs. Therefore, the current focus is on developing an adapter that links the vision encoder and the LLM to enable cross-modality interaction. To construct effective LVLMs using pre-trained and unchanged vision encoders and LLMs, the key challenge lies in the design and training strategy of the adapter. Some existing methods, like Flamingo and AnyMal, use the perceiver resampler as their adapter architecture, which has proven to be an effective solution for cross-modality interaction. Meanwhile, PaLM2 addresses the adapter pre-training challenge by introducing Q-Former, which involves an additional pre-training stage with multitask learning on image-text pairs. Although these approaches have shown impressive results, the question of what the optimal adapter architecture is and whether pre-training the adapter is necessary remains open for further exploration. To delve into these questions, we conduct a thorough investigation of the latest cross-attention-based adapter architectures, especially focusing on the perceiver resampler, and establish a strong baseline. However, we noticed that the perceiver resampler adapter faces issues with slow convergence and limited scalability, particularly when increasing the size of the vision encoder. To address these challenges, we introduce PaLM2-VAdapter, which utilizes a progressive alignment strategy to connect unchanged vision encoders and LLM decoders. Specifically, we apply the classic alignment framework progressively in 2 stages, and train a tiny PaLM2 model to serve different roles. Stage 1, as an LLM decoder, Stage 2, as an adapter. Compared to baseline models that use state-of-the-art adapters, our PaLM2-VAdapter achieves faster convergence, higher performance, and better scalability, as detailed in our results. We evaluate our models on a variety of vision language benchmarks, including tasks related to image-based and video-based captioning and question answering. Our models consistently deliver top-tier or comparable performance, while requiring 30 to 80% fewer parameters than previous models. This efficiency highlights the effectiveness of our proposed PaLM2-VAdapter in advancing the LVLM field. To summarize, our contributions are threefold. We provide a comprehensive study of the state-of-the-art adapter architecture, particularly the perceiver resampler, and establish a strong baseline with it. We propose PaLM2-VAdapter, a novel progressive alignment strategy to train a tiny PaLM2 language model as the vision language adapter, significantly improving convergence, performance, and scalability. Lastly, our models achieve top-tier performance on various visual captioning and question-answering benchmarks, all while using significantly fewer parameters than other models. Section Summary. In this section, we explore the advancements in constructing large vision language models, LVLMs, by integrating vision encoders and large language models, LLMs, without the need to develop them from scratch. Recent research focuses on freezing both vision encoders and LLMs during LVLM training to prevent catastrophic forgetting and reduce training costs. We introduce PaLM2-VAdapter, a progressive training strategy that bridges frozen vision encoders and LLM decoders, demonstrating faster convergence, higher performance, and stronger scalability in various vision language benchmarks with 30 to 80% fewer parameters than previous models. Section: Large Vision Language Models, LVLMs. In this section, we discuss Large Vision Language Models, LVLMs, which are advanced systems designed to bridge the gap between visual and linguistic information, thereby enhancing the reasoning capabilities of language models to interpret and process inputs from both modalities. Various approaches have been explored in this field, including notable models like Flamingo, BLIP2, InstructBLIP, MiniGPT-4, and LLAVA. These models primarily differ in their design of adapters, training methodologies, objectives, data used for training, and how they are fine-tuned with instructions. Flamingo stands out as the pioneering model in this domain, employing a perceiver resampler as an adapter to integrate visual tokens into language models. Despite its innovation, Flamingo's architecture comprises billions of trainable parameters, which somewhat hampers its efficiency. On the other hand, BLIP2 introduces a more compact adapter known as the Q-former, which, despite its lightweight nature, requires a complex training regimen that includes a two-stage process with three distinct training objectives: vision-language contrastive loss, matching loss, and generation loss. Building upon BLIP2, both InstructBLIP and MiniGPT-4 extend its capabilities through the use of instruction tuning data or an additional projection layer. LLAVA simplifies the process by employing a straightforward projection layer to align vision representations with the language dimension. In our work, we propose a novel approach that leverages a pre-trained language model as the adapter, demonstrating faster convergence, improved performance, and enhanced scalability compared to the state-of-the-art perceiver resampler. Our methodology is grounded in a classic visual language alignment pipeline, which maintains the visual encoder and the large language model, LLM, in a constant state, with an adapter inserted between them to map the encoded visual embeddings onto the language representation space. This section provides a preliminary overview of vision-language adapter architectures, explains our model framework with an adapter, and introduces our progressive vision-language alignment strategy for training a tiny language model as the adapter. We delve into the exploration of state-of-the-art cross-attention-based adapters and propose a novel approach that progressively trains a self-attention-based language model. Self-attention layers in adapters can enhance the quality of representations, and initializing these adapters with pre-trained language models can lead to better convergence and performance improvements. Our vision language model comprises three main components: the vision encoder, the visual adapter, and the LLM. The goal is to align visual features with the LLM representation space, with both the vision encoder and the LLM remaining unchanged throughout the process. This setup significantly reduces training costs while preserving their robust visual feature extraction and reasoning capabilities, thanks to extensive pre-training. Specifically, the vision encoder, pre-trained with image-text pairs, converts images and video frames into feature tokens, which are then mapped by a lightweight visual adapter into the LLM representation space. We utilize PaLM2 series models as the LLM decoder, with the training task focused on generating captions based on the visually embedded prefix. To further enhance vision language adapters, we introduce a tiny PaLM2 language model, employing a progressive alignment strategy. This method involves two stages. Initially, the language model, starting from a pre-trained tiny PaLM2 model, is fine-tuned with classic vision language alignment tasks. Subsequently, an additional layer, a perceiver resampler, is added to bridge the same vision encoder and a larger PaLM2 model, showcasing faster convergence, superior performance, and greater scalability compared to the leading models with state-of-the-art adapters. This progressive alignment strategy, coupled with the effective architecture, significantly advances our PaLM2-VAdapter, achieving remarkable improvements in vision-language alignment. For implementation, we use COCA pre-trained vision transformers, VITs, as our vision encoders and PaLM2 pre-trained models as the LLM. The adapter architecture in our proposal includes a one-layer perceiver resampler and a tiny transformer-based language model. Our models are trained on datasets featuring image text and video text pairs, with specific details on training parameters and evaluation metrics provided for a comprehensive understanding of our approach. Section Summary. In this section, we explore the advancements in large vision language models, LVLMs, that bridge vision and language processing, enhancing reasoning capabilities through various adapter designs and training processes. Our proposed progressive MENT strategy introduces a pre-trained language model as an adapter, demonstrating faster convergence, improved performance, and enhanced scalability compared to existing methods like the perceiver resampler. By utilizing a tiny PaLM2 language model in a progressive training approach, we achieve significant advancements in vision-language alignment, leveraging self-attention layers to enhance representation quality and utilizing pre-trained language models for better convergence and performance. Section: A strong baseline with perceiver resampler. In this section, we delve into the effectiveness of various components within cross-attention-based adapters by conducting a detailed study using the perceiver resampler, which is at the forefront of adapter architecture. Our investigation spans several aspects, including the application of layer norm, key modules such as the feed-forward network, FFN, and time embedding, the dimension of queries and cross-attention layers, and the number of perceiver resampler layers. From our findings, we've distilled a few design principles for adapters based on the perceiver resampler. Firstly, applying layer norm separately to queries and cross-modality inputs, keys and values, is crucial. Secondly, incorporating an FFN and time embedding not only stabilizes training but also significantly boosts performance. And thirdly, it's beneficial to maintain a moderate size for the learnable queries and cross-attention layers. Following these guidelines, we've established a robust baseline, achieving impressive scores across various benchmarks. Despite the baseline's commendable performance, we noticed its scalability and convergence speed were lacking. To tackle these issues, we introduced a tiny language model as an adapter and opted for progressive training. This approach led to our PaLM2-VAdapter outperforming the strong baseline in terms of faster convergence, higher performance, and stronger scalability. Specifically, our model converges approximately 3 times faster, demonstrates superior performance with the same vision encoder and language model decoder pairs, and exhibits more significant improvements when scaling the vision encoder. We also explored different pre-training strategies for the adapter, comparing a randomly initialized approach, generative pre-training on language data, and our proposed progressive training strategy. The latter involves initializing the tiny PaLM2 model from a checkpoint and then fine-tuning it with vision-language generative pre-training. Our findings confirm the effectiveness of this progressive training strategy, which combines language-only generative pre-training with vision-language generative pre-training. Despite the advancements, we found that the perceiver resampler remains an essential component for enhancing cross-modal alignment and performance. Initially, we used an attentional pooler for cross-attention in our first vision-language alignment stage. However, our in-depth empirical study led us to replace it with a one-layer perceiver resampler, which proved to be the optimal choice for cross-modality fusion in our PaLM2-VAdapter, contrary to the performance plateau observed with additional resampler layers in other designs. In terms of visual captioning, our method showcases competitive image captioning capabilities on the COCO dataset, requiring significantly fewer parameters compared to the state-of-the-art ModelMakes model. This underscores the efficiency of our progressive training strategy. Furthermore, our model scalability is evident from the vision encoder scaling experiment, indicating that a more potent vision encoder enhances image captioning performance. We provide qualitative examples to illustrate these points. For video captioning, our approach demonstrates solid improvements on the MSR-VTT and VATEX datasets compared to leading models, again with a fraction of the parameters. This improvement is consistent with the image captioning results, showing that scaling up both the vision encoder and the language model enhances the model's ability to interpret sequential visual information in videos. Qualitative examples further support these findings. Section Summary. In this section, we explore the effectiveness of various components in cross-attention-based adapters through a detailed ablation study using the perceiver resampler architecture. Our study reveals key design rules for adapter performance, such as the importance of layer norms, feed-forward networks, and moderate dimensions for queries and cross-attention layers. By following these rules, we establish a robust baseline achieving high performance on captioning tasks. Section: Visual Question Answering. In this section, we delve into the realm of visual question answering, focusing on both image and video question answering capabilities. We put our method to the test across several datasets, including VQA-V2, Text VQA, VizWiz, and OK-VQA for image question answering, and MSR-VTTQA, MSVDQA, and IVQA for video question answering. Our findings reveal that our approach, while utilizing significantly fewer parameters, only 14% of what the state-of-the-art IBELICS and Flamingo models use, 10.8 billion versus 80 billion, manages to deliver comparable, if not superior, performance. This underscores the efficiency and scalability of our method, particularly of the PaLM2-VAdapter, which consistently improves as we scale up the vision encoder and the language model, LLM, decoder. We've included some qualitative examples in our figures and appendix to illustrate these points. However, we also discuss some limitations and areas for discussion. Our PaLM2-VAdapter marks a leap forward in terms of efficiency, requiring far fewer parameters and reducing training costs. Yet, as we scale the LLM decoder, we encounter challenges similar to those faced by other large vision language models. The crux of these challenges is ensuring that visual embeddings can be smoothly integrated into the input representation space of the scaled-up LLMs. We suggest a potential solution might be to directly convert visual embeddings into language tokens, using a shared LLM codebook across different model sizes to facilitate zero-shot transferability. To explore whether visual embeddings can be effectively translated into words, we conducted a study. We added a fully connected layer after the adapter and employed the Gumbel softmax operation to quantize the visual embeddings into a sequence of words, which could then serve as a prefix for the LLM decoder. The output logits from this layer are matched to words in the LLM codebook, with the highest logit determining the corresponding visual token. Our results, however, indicate that training the Gumbel softmax operation is quite challenging. Despite extensive experimentation with hyperparameters to stabilize training, the best outcome we achieved was a 15.3 CIDR score on the COCO captioning dataset, with a softmax temperature set at 2.0 and subject to exponential decay. This represents a significant drop in performance compared to the baseline where visual embeddings are not quantized. It suggests that while visual embeddings may occupy a similar representation space as the LLM codebook, a straightforward translation to words is not feasible. This insight opens up an intriguing avenue for future research, enhancing the encoder and adapter's zero-shot scalability to larger LLMs.